Hello. So today I want to talk a little bit about functional forms, and in particular finding optimums and in-between limits, which is useful in spacecraft design calculations. So let's start off by plotting some function which in this case is a function of x between the limits of 0 and infinity, and the function that we're going to use is a nice simple one, which is 1 over x. And so it kind of looks, if you were to plot this, it looks a bit like this. And so when we look at this, we can look at the limits and use the appropriate language in mathematics. So we can say that, for example, in the limit, as x tends to 0, so this is x tending to 0, we can say that f of x tends to infinity. Similarly, we can say that in the limit, as x tends to infinity, so x is getting larger, the function of x tends to 0. So this is a useful thing to plot. To demonstrate an example where you might see this kind of functional form, we might have a plot of two spacecraft parameters, and we were going to call them the mass of the payload, it's the spacecraft payload, and on the x-axis the mass of the propellant, it's the amount of fuel, and this might have a 1 over x relationship. So again, we can see that the function of x is equal to 1 over x, but now using the correct language that's appropriate to the graph, we can say that the mass of the payload, and we're going to use the approximately equals sign because there's often other factors that come into it, approximately equal to 1 over the mass of the propellant. So if, for example, we had a mass of propellant that was equal to 10, and that might be tons, for example, 10 tons of propellant, therefore you can see that the mass of the payload is going to be about 0.01, which is 1%. So this is a payload mass fraction of 1%. Another example we might think about is a nuclear pulse detonation, where we can define a parameter f hertz, which is the pulse frequency of detonation. That's the number of, say, capsules of material you're detonating per second, which is equal to the total number of detonations divided by the burn time, how long we're burning them for. So this might be, for example, 1 year acceleration profile, and this is also equal to the total mass of propellant divided by the mass of material, which if it was ICF, we might be talking about small capsules, small pellets of material, times by the burn time. And then we can say that if we had a constant propellant mass, just make that assumption for this exercise, we can say as the number of capsules, the mass of the capsule tends to 0, so in other words we use smaller and smaller capsules, or smaller and smaller pieces of material or fuel to detonate, that the pulse frequency of detonation tends to infinity. And this is a bit like tending towards, in the limit of a non-pulsing system, what's called continuous thrust. And similarly, we can say as the mass of the capsules tends to infinity, they get larger, that the pulse frequency of detonation tends to 0. So we're using less of them because they're bigger. And this is very simple to what's known as external nuclear pulse detonation, such as used in Project Orion. This was a famous project from the 1950s and 60s, which involved detonating nuclear explosives. And so in that case we can see they get larger, and so the pulse frequency would be quite low. It would be something like between 1 and 10. Where in this situation, because the pellets are so small, they might be milligrams or even micrograms in size, you may be detonating thousands of them per second, and so it's tending towards a non-pulsing circumstance. Continuing with another example, let's now think about, again, plotting a function that looks again like a 1 over x function, and this time we're plotting the burn time, TB, which might be in years if we're talking about interstellar, for example, or it could be weeks or months if we're talking about interplanetary. And we're plotting this as a function of the pulse frequency, which is measured in hertz, 1 over seconds. Now, the actual total flight time of just a flyby mission is equal to the burn time, TB, plus the cruise time. And so if your burn time is overly long, it's taking you much longer to get up to the velocity that you want to get up to, then obviously this is going to elongate your mission profile. So your total time could also be much longer. Now, the actual mass flow rate of fuel in your engine, m dot, is equal to m cap, where cap is your capsule mass or fuel mass that you're detonating, times by the pulse frequency of detonation. And so we can rearrange this as the pulse frequency of detonation is equal to m dot divided by m cap. And similarly, we can also say that the burn time, as we saw earlier, is equal to the number of capsules divided by the pulse frequency of detonation. So it's inversely proportional to the pulse frequency. And so again, we can plot this as follows. So this is F hertz against the mass of the capsule, and this also is a 1 over x kind of relationship, as you can see. So looking at our top graph, we can see that for large pulse frequency the burn time will be reduced, and for lower pulse frequency the burn time will be elongated. And similarly for the bottom graph, if we have a large capsule mass, the pulse frequency will be less, and we have a small capsule mass, the pulse frequency will be higher. And if we were to take these two graphs and plot some median points between them, You might get something like this. And then in between there is going to be some other point, which we will call an optimum. So it's an optimum between these parameters. And this is something we're often interested in finding. What is the optimum between the capsule mass you want to use and the pulse frequency? What is the optimum between the pulse frequency and the burn time? And let's now just finish off with one other example. So this time we're going to plot a different parameter. And this is something called the jet efficiency. And if you want to know what that is, that will be explained more in other lectures. And we're going to plot it as a function of the burn-up fraction. But essentially, the jet efficiency defines how efficient your engine is, how much of the power that's generated inside the engine is converted to useful work in the jet of the exhaust. And it's defined as a ratio. And the burn-up fraction is how much of your fuel you're burning. So if you had ICF capsules, for example, or some other quantity of material, how much of that is being converted into energy that you can actually use for useful work and generation of thrust. And it turns out that these are given by an equation which was derived by me, but the jet efficiency is equal to the exhaust velocity squared divided by 2 alpha phi c squared. And alpha is the mass defect, so if you're talking about fusion, it's how much of that reactant is converted into energy in the conversion into the product. And this is your burn-up fraction, this is your speed of light c, and this is your exhaust velocity. That's the velocity of your jet that comes out of the exhaust stream. And it turns out that when you plot these, they are inversely related in a 1/, kind of x relationship again. And so as a result, it is the case that for a higher value of burn-up fraction, this will imply a lower value of the jet efficiency. And similarly, for a lower value of the burn-up fraction, it will imply a higher value of jet efficiency. And what this means is that if you have a more explosive detonation, because you're using up a lot of the energy that's in, say, a capsule, you're getting as much energy out of that capsule as you can, the more explosive detonation probably means you have a less collimated jet beam, and so you're losing power, and it's a less efficient engine overall, although you're getting more energy out of the individual capsules. And similarly, if you had a highly efficient engine, so you don't have much power loss, this will happen, but by implication of this graph, you probably won't have a very high burn-up fraction. So there's a compromise here between, say, getting a high burn-up fraction but for low jet efficiency, and getting a high jet efficiency but for low burn-up fraction. And that compromise is the optimum. So this is our optimality point. And this is the kind of thing we're interested in finding. And the optimum is really between these two median points on the graph. So that's just a little discussion on thinking about the limits. As you can see on this graph, as phi tends to infinity, jet efficiency changes in such a way that it goes down. And so it's important to understand that when you're looking at graphs or when you're looking at equations, you should be able to see what's going to happen and understand physically the relationship between the parameters and what it implies in terms of the performance of the system you're looking at. That's it.